at all right now.
Are you sure we want to be using a quoted list for that? Okay, you're not going to be like modifying that in place at all?
I believe I am, but there's
I mean, as long as we don't use any destructive list modification operations, it should be fine.
Yeah.
Hello?
Yeah,
being a little faster can't hurt.
So what I want to do is I want to define a function called cell index, which is going to take a stage and a position in that stage. And what I want it to do is I want it to, if I pass it in an x and a y coordinate, I want it to actually return the index into a flat one-dimensional array. And we can do that with just a simple little bit of math. We'll do width of the options of the stage. And you can accomplish that by doing, if I can remember correctly, plus times y width or y height.
Y width.
Sorry to interrupt, but I just want to mention to folks who are watching the live stream right now, there was some technical difficulty earlier. I was noticing on the live stream. It rebooted and cut off about a section, but it's not just around the time that you were defining the cell object. So it looks like we're back live, and it will be separated into two separate videos because of it. So I do apologize for the inconvenience.
Stuff happens. Mm-hmm. Okay, so yeah, we just defined a cell index function, which takes a 2D coordinates x and a y and converts it into our.
Is there any particular reason why we aren't using just a 2D array for this?
Yeah, we'll see later.
Okay.
I'm trying not to get into explaining too much right now because
fair enough.
There's just a lot to it.
If we don't get to that by the end of today, I'm going to ask you later, though.
Okay. And so we want a function. We have our features list up here, which is just a wall right now. But eventually, we're going to add more features to this list. So we want to do a little bit of, I guess, set theory, basic stuff. We want to check if a feature is present. So we'll just call it feature present p. It's going to take a cell and the name of the features as a symbol. And, just going to use member feature of cell features. And that's just going to, check it if a cell has a particular feature. We also want we want to be able to add a feature. Yes. Feature, and I guess we'll use definitely push new for this. And if you're not aware, push new is just going to ensure that the same symbol is not pushed to the list twice. And you can supply the test function for that, as with most of these functions or macros. This is a macro. So push new feature to the same list, cell features of the cell. And we also want to remove a feature. Finding all these now because they're going to be highly useful later as we start carving the properties of our map out. And this, I believe, is in our AFP utils function provided by Alexandria. I believe F. Yep. Cell features of the cell and our feature. And what I mean by feature here is just a symbol. All these are taking a symbol. Like you would actually pass, colon wall or colon whatever. And this is going to delete from the cell features list and modify it, whatever features passed into it. We also want the intersection. Of, I guess, yeah, however many features the user passes in, or our algorithm passes in. So we can use the Common Lisp intersect. Yeah, that's it, right? Yep. Intersection features. And if you're not familiar with these functions, you can just, they're pretty simple. Just some basic set theory stuff. It's right up on the hyperspec if you want to take a look. The only thing we're not doing here is unions, which doesn't really make sense. Cell. So that should be all we need for features. And we want to create a cell. Did we make our make cell function yet? No, we didn't. Let's stick this somewhere. That's going to take the same thing. And index is going to be cell index. And this is going to be a destructive operation. We're actually going to modify the array of our grid of our stage. And it's going to call our low-level mixed cell. Should be correct. Let me test the whole thing all together. And we can see our grid filled with a bunch of cells, and they all have wall symbols. Cool. And you can see they all have different positions in space. And there's a lot of them. 49 times 49. What is that? Wow. So yeah, we created the basis of our, our data structure. The next step, this is the complete first step, which might be a good stopping point. I don't know. I could go on farther if you want to go on farther, Ram. It's up to you.
Let's go until 7:30. I think we're getting close to getting done with Make Grid, so we may as well finish off Make Grid.
So that's done. That's completely out of the way. We can collapse that. Carve Rooms is when we actually carve out the rooms, and what we're going to be doing is we're going to be removing the wall property from certain cells. And to actually have a picture, we're going to be doing that. We're going to be choosing random positions on our array and filling them in with randomly sized rooms. And remember how I said that the constraints of the stage are that it must be odd and odd width and odd height? The same is true about the rooms for this algorithm to work. Rooms must also be odd-sized width and height. And we'll see why. Well, actually, we can kind of see right here. And that is because if we started at the, the first column in the first row, it's going to guarantee that it always ends up one less than the end of the last column and last row, and that no rooms are ever going to touch each other, which is important later. And that's the only reason why we have those constraints. We don't want any overlaps. We don't want any adjacencies, rather, and we don't want rooms to touch the edge of the map. We always want a 1 pixel or 1 cell border. That's why those constraints are in place. And the next step of our algorithm, the adding the rooms part, is actually, well, I would say it's about the same amount of code as what we just did. Except it's all localized into a single file, so we don't have to jump around as much. But most of it consists of, enforcing those constraints and doing a heuristic to allow the user to pass in a percentage of the map to fill with rooms. Like we could say 10% and there would be less rooms than this, or we could say 100% and there would be mostly the whole map would be filled. And at the same time, we want to ensure that it's always terminating. We don't want it to be an infinite process. So there's some logic involved with that, but nothing too complicated at all. And that's what we'll be doing next stream. And once we have that, that's probably not too much code, not too much time. We could probably work on the next section, which is going to be carving the corridors. And for the corridors to be carved, what we're going to be doing is we're going to be mapping over each row of our map one by one. And whenever we come across a cell that is not a room, which would be the first cell here, we're actually ignoring the borders. Borders are always staying as borders, which would be, the first cell in, up and down, or left and right and up and down. Right here, this cell right here, we come across, we see that it's not a room. So what we're going to be doing is we're going to be starting a maze algorithm, starting from this cell. And it's going to fill in everything. It's going to go down here and fill in this and fill in this. And if the stage is dense enough, it's going to take a few maze algorithms to fill the whole complete map up. We want to keep going until the whole map is filled with mazes. And it's going to look like this when it's done. Okay? And then after that is the connection of the regions. And what I mean by region is every room is going to get a distinct region. We're going to start incrementing an integer from 1. So like say this is the first room, it'll be 1, 2, 3. And when we do our maze algorithms, every distinct maze is also going to be a distinct region. And that's going to continue from the last room's integer. And we're going to basically give each room in each maze its own region. So that when we do step 4, wow, that's not step 4. Step 3 is missing in my pictures. Step 3 is basically we're determining whether, we're looking for cells with adjacent distinct regions. Like this cell right here, this black cell right here, is going to be what's called a connector. That's the terminology I used. It's going to be a connector because both the left and the right neighbor of that cell are different regions. Now, this right here is not a connector because it has to be both the left and the right, or both the top and the bottom.
So
and that's
question
important
there,
because basically a connector is going to be a potential door in the future.
So question, because this is an interesting point. Based on your definition, wouldn't any of those 3 pixels there in that neighboring region that your pointer is at be a connector?
So 1, 2, or 3?
Yeah.
Yes. However, let me check really quick to answer that.
Because it looks like that based on what you just described.
Just a second, because that's a good question. I know the answer is no, but I'm trying to give a proper reason. Okay, so we're mapping over the whole stage. We're filtering out all the connectables, and those are the orthogonally adjacent neighbors with different regions. Okay. So, yes, they would be. I was wrong. Okay. The answer is yes. All these would be. Do I have? Actually, I think I have a picture. If I pull up my old Trello page, have a picture. No, I don't. Nope. Sorry, I don't have a picture of the connectors for you.
All right.
But basically, yeah, there's going to be, we're gonna make this a connector, this connector, like you said, and all the other ones. Okay, and then the last step, or actually, not the last step, is carving the junctions. And a junction is just a name for what could be a door or a doorway, or whatever you want, whatever the user wants to connect the regions together as. You could even mix and match. I mean, they don't all have to be doors. You could have hallways and doorways or whatnot. But basically, a junction is just that, whatever the user wants to use. The last step, and junctions are that's complicated. Basically, what we're doing is we're going to be computing a minimum spanning tree using graph theory, a nice little graph library with Common Lisp, which is awesome. I'll explain it as we do that step, which will probably be the session after next. And what that's going to do is it's going to define a minimum spanning tree, which is, if you aren't familiar with graph theory, it's going to be, there could be many minimum spanning trees in a graph, and it's basically going to ensure that every region is connectable through one point. And then on top of that, we're also going to add loops to make it not a minimum spanning tree. It's going to be an actual graph rather than a tree. Because, am I correct on that, Elijah? If you have loops, it no longer becomes a tree. Yeah, that's right.
Yeah,
no,
that's right.
Correct.
That's correct.
Technically, a tree is a graph, but it has no cycles.
Yes.
Right.
So.
Yeah. So what we want to do is we want to.
It's a directed acyclic graph. Right. Well, a tree is a subset of directed acyclic graphs.
It's not directed. So a tree is a graph. It doesn't have cycles. Unless you add direction, it's not a DAG. So.
Well, I mean, in general, when you're doing a tree, it would be a DAG just because you have a direction that you created the tree in.
What you're saying is true. I'm just saying generally from a graph standpoint, if you're starting with a graph with undirected edges, you're going to end up with a tree, which is just a graph with no cycles, assuming that the graph is an undirected graph. Anyway.
Right, but the way that you compute the minimum spanning tree enforces a direction.
Right.
I'm going to stop sharing for a minute to jump to another monitor really quick. I want to try to find a picture to better illustrate this for you guys. So I'm not going away. I'm just stopping my share really quick.
Absolutely.
So I can figure out how. Am I still screen sharing right now, or no?
Nope,
no, you're fine.
You're good.
Okay, good.
Doing the minimum spanning tree operation produces a direction. You may not bother to record that direction anywhere, but technically speaking, you have produced a direction. Because trees always have a most ancestor node.
Right, that's true. That's a good point. It's just
technically, although actually, now that I think about it. With a minimum spanning tree, you could pick any node to be the root node.
Right.
And the direction flows from that node. So I mean,
and what we're going to be doing is we're going to be choosing a random room, and that room is going to be the root node. And then, after the minimum spanning tree is created, and all the loops are created, we're going to be choosing the room that is farthest away from the root room. And we're going to be marking that as the exit.
So I just have a question. Why are you doing it in two phases? Is it by connecting the rooms with the doors? Aren't you already kind of generating a graph, or are you not generating a graph by doing?
Well, this way you can guarantee as a first step that the whole thing is connected.
Okay. That makes sense.
That is correct.
Okay, so you're doing the connectedness
and then we're going to be
first.
introducing imperfection,
if you just carve out random spots, there's no guarantee you'll end up with a connected graph, or you may go too far.
True.
Right? The idea is we want to start off with the minimum required to make it connected, and then start adding extra stuff onto that so that it looks more interesting.
Okay, so you're essentially guaranteeing connectedness so that you have some sort of path to an end goal. Okay.
Yep.
All right. Gotcha. Because technically, a disconnected graph is a graph with four.
Yeah.
It just has zero edges. But I just want to make sure that that wasn't the intention.
Correct. Yeah. The idea is to not is to have a connected graph. And so starting with computing a minimum spanning tree
is better.
Forces that.
Right. Okay.
Well, adding edges until we have a minimum spanning tree really is what we're doing.
Okay, so it looks like I'm not going to be able to find the image that I wanted to show, but it just better illustrates the whole algorithm and steps, with including the connectors that you were questioning. But
this is certainly a good stopping point, Michael. Just because
we add that next week. Yep.
We went through a lot of ground here, especially your earlier algorithms and the design and use of structures. I have to really review the use of structures. And
I might actually change this to just use classes next week, just to make things simpler, especially if you guys are going to be messing with the code and maybe defining new slats and wondering why things are breaking like it did for me today.
Oh no, certainly. I think it's a good point though. I mean, there are some advantages of using structures versus classes inside Common Lisp, and I think this is certainly probably a good application for it. I don't know if there are cases, and I don't think there's
not too many good reasons to use a struct. Like you see here how I'm using a conc name of nil.
You're not streaming.
You're not streaming. Share your screen.
And we're back.
Okay, so you see how I'm using a conc name of nil, and I do this for pretty much all 3 or 4 of the structs that I defined today.
Yes. Mm-hmm.
If I had another struct besides options that also had the width or the height or the seed slot, that's going to collide. It's not going to be like class where it's going to dynamically dispatch based on the argument. It's not going to be an accessor. It's going to be an actual slot value.
Gotcha.
They're gonna. It's basically you're generating the name of the accessor with a combination of the conc name and the slot name. By not having a conc name, you're just calling the accessor width.
Earlier, I was wondering about that because you were using width directly, and I was like, wait a second, wouldn't it be options width? But I wasn't sure if it was because you made that nil or not, so that makes more sense.
I make a lot of bad style choices when I use structs in favor of brevity, but it's what it is. It's not something I really wanted to explain or get into, but because it's just not it's not good practice to use structs.
Gotcha.
That's the gist of it.
Yeah, I use structs when I have, and even then I don't use structs very often. But when I use structs, I use them when I have very small value types that I know that are not going to, be changed or need any funky behavior or validation or anything like that.
Even then, even if you use structs, though, you would want to use the struct name instead of doing conc name nil, right? You'd want to actually have something so that your slots
in general, you don't use conc name nil unless you really know what you're doing. Because the accessors for slots are just regular functions. They're not generic.
Right.
And so they will clash.
So yeah, I'm just mentioning it because if folks are watching this, right, obviously this is an important point, right? You could use structs certainly, but this is the style here is not necessarily the best thing unless you know what you're doing exactly.
Yep. So really, the thing with structs is that there are a lot of pointy edges using structs. There are a lot of little places where you can, really work yourself into a confused state or a confused image or, just confused self, to be honest. You can confuse yourself pretty easily using structs. So I will use them when I need something that I know if I have a 2-dimensional point, right? I will prefer using a struct for that as opposed to using a vector of length 2. Though that way I still get the type check that this is a point because it does actually tell me, and I get the nice accessor functions. But I know that I'm not going to ever be giving default values for that, or it's not suddenly my 2-dimensional point is going to gain another dimension anytime soon, or any of that stuff. And there's no complex logic defined for what is a 2D point, And so in that case, I might use a struct, but even then, there isn't a lot of reasons why you need to use it unless you really start hitting like performance, sensitive code.
Right, and that's the other case where I was kind of curious about. Like, I'm assuming that they do packed alignment in structs guaranteed, but is it?
It depends on a lot of things, actually.
Okay.
SBCL. So firstly, it depends on if you've declared the types of your struct and if you're using value types. So numbers or characters, right? Because there aren't any other value types in Common Lisp.
Right.
Like it can't inline another object. It just can't. Because you might then pull that object out, store it in a variable, and mutate it, and or like assign it somewhere else, right? And then it has to do a full object copy, and that's just not really well defined.
Right. I just assumed that packed alignment practices, at least in Common Lisp, is for objects. Like if you have nested objects or you're doing object composition, it's going to be a pointer. It'll be a cons to another location almost, and behind the scenes
it'll be a pointer.
Okay.
If you have an object containing another object, the first object will contain a pointer to the second object. If you have an object containing a number or a char, it'll probably inline that. It'll probably just have the number or char inside the struct and use the type info of the struct to know how to parse that back out again.
Okay.
But if you've got pretty much any other type, it won't bother. It's just going to use the pointer.
Gotcha.
That's pretty much it.
It's fairly consistent with other garbage collected languages. I'm pretty sure actually Java does the same thing behind the scenes. So
pretty much.
It's not a surprising thing that what you're saying there. I was just kind of confirming what my suspicions were, but I should really dig into SBCL a little bit more to understand.
Digging into SBCL is a chore. If you want to do it, you're free to. I've already put in the work, so feel free to ask me the questions.
Gotcha.
I have spent way too much time decompiling random stuff in SBCL to see what it's actually doing. But anyway.
We sidetracked. So, Michael, what are you kind of showing us here? This is your game badge.
Oh, I was just going to mention that I only use structs in two cases.
Mm-hmm.
The first case we've seen, and that's when I want to, see all the slots and values in the inspector at a glance, which is not a very convincing case for using structs. The other case that I use it is when I'm using the type argument of def struct to specify that it's actually a vector or a list.
Gotcha.
Structs allow you to specify the type of the struct. So this is going to actually, if I were to make an instance of this struct called vec, it's actually going to become, at compile time, it's going to compile into a vector, rather. And that is important because it's no longer an object. It's actually an array, and you can have fast integer math on it, or no number math on it.
That's actually pretty
nice.
In
this case.
So this is almost like a type alias, actually, with named.
Well, this is the type alias.
Yeah.
Well, this has nothing to do with it. It would still work without this.
Yeah.
Okay.
The only reason why I have that type alias up here is so that I can declaim the f type to be that rather than, some long, simple array, single float.
Yeah, but what I'm saying is what that object construction behind the scenes, this effectively is generating a type. It's compiling a type from an object construction, right? It's a type. It's the same thing as a def type almost, right? I mean, it's not.
Well, so let's stop right there. Def type. And this isn't really the day to go into the type system, but def type doesn't do anything. Def type does nothing magical at runtime. Literally, all def type does is add another rule into the type system so that when it hits a vec type, when you declare something to be a vec type, it expands that to whatever you specify in the def type form. It's just a macro, really, but in the type system. It's just a macro. It doesn't like declare layouts. It doesn't, make new objects. It doesn't make classes. Like, you can't use a def-typed type in a method in a generic function because def-type does not create a class. And methods need to be specialized on classes, not on just arbitrary types. Def-type just creates a type macro. It's just an alias. It disappears. It disappears very quickly. Def-struct does create a class in principle, although if you pass the type argument, it probably doesn't, because there is no runtime type info there anymore. It's just a vector. When you tell def-struct to make me a vector, that actually is creating that actually is basically just making a new vector constructor that's specifically a 3-argument vector constructor, and
So there's actually a very interesting property of defining a struct with a type of vector like this. And that is, well, not only do we see that it's actually a vector when we construct it, however, it also allows us to, access the array with the struct names as accessors rather than using aref. And you want to know the best part about it? On SBCL, it compiles to the same assembly code as using aref directly. So you get named accessors to your array for free.
Yes. However, I would like to point out that if you don't bother using type there and you just leave it as a regular struct, you get the same thing. It's just you do have the extra overhead of storing different type tagging info, and you can't use aref or pass this directly to things that expect a vector. Right, so it's not a vector anymore. Haha.
Right, it's a proper object at that point.
Right, but my point is that layout internally, it is pretty much exactly the same, and the accessor is compiled to pretty much exactly the same code. And actually, SBCL, if you declare the type,
let's test it out. Hold on.
Yep.
So,
oh god, we're gonna disassemble stuff.
We're gonna make a function. It has to be a function to disassemble, I believe.
Yep.
Disassemble. Wrong one. What did I
actually do? If you'll give me a moment, I could take over at this point since I have some nice stuff for doing disassembly.
Yeah, there we go.
Okay, well, just a sec. Let me see here.
Yeah.
I'm curious myself. So 93 bytes, and that's... Oh, it's not the same anymore. It used to be. Unless I did something wrong.
114. There is some extra overhead there, but...
And that's on the aref.
Yeah.
The actual struct... Oh, you know what?
Hairy data vector ref. It is not being as clever as it needs to be. Is what's going on there.
What would happen if I did like...
is make the internal constructor?
Yep.
Or is make a constructor you wrote?
That's the internal.
Okay.
Okay, that makes a bit more sense because it's a car. But...
oh yeah, it's not even... you see what it did?
It's not even close.
It didn't even create the array. The array doesn't exist. It did the aref at compile time and inline the 1.
Yeah.
Nice.
I love SBCL.
Oh, it really does some clever optimization sometimes.
It's like, oh, you've got a constant array here. Let me just handle that for you.
Yeah, and that's why you don't use literals, hooks.
Where the heck?
Okay, 106 bytes versus 93 bytes is what it looks like.
I'm confused because that used to be the same assembly.
Give me just a moment. MREPL, make sure I'm in a nice clean package.
I'm on the very latest SBCL.
Yeah, in package CL user. Synchronize that.
Oh, I'm on 1.49. I'm kind of curious now.
This.
Let's see here now.
P. Okay. Michael, do you mind if I take over for a minute?
Go ahead.
Okay.
Second.
Screen share. Hide that stupid thing. If it'll let me. There you are. Go away. Okay. 4. That a little bigger. Can you guys see?
Yeah. Just a little bit bigger.
Okay. That better?
Yeah, that's better.
Okay. Let me see. Where was I? Destruct. Let me just first do this with the vector. A vector single or simple array single float of 4 elements is going to give us an aref a2. What does that generate? Oh god, why did it do that? Here we are. I have magic. Yeah. So I have this little tool here called IDIS, Interactive Disassembler. This right here is optimization settings. This is speed over everything else. And then I can, give a lambda list, roughly a lambda list, but I can basically give sort of like def method, but I can give types. And then I can just do stuff in there. And then when I compile this, it hops me over to my inspector here, and I get to see the disassembly, just right in line there. So where was I?
I'm actually curious why I'm not seeing the same assembly anymore. If you could figure that out, I'd be pretty amazed.
Well, let's see what it looks like. Vector single float 4, right?
It's actually 3, I think, in his
3.
implementation. Yeah.
Simple array. I'm paranoid about that. I always do simple array single float. X 0 0 type single float.
Yep.
That's what you're doing, right?
Yep.
Okay. Let's see. Oh, you have to use a vector.
Yep.
Okay.
It can only be vector or list.
Fair enough. How many elements in single float? Oh, and you can't even give the length?
Nope.
I dislike the type system sometimes. Okay, so if we compile that, oh god, what have I done now? 3. There. And if we say vector single float, that's what we get. And we get a hairy data vector ref. Right. It just calls into the SBCL internal nonsense for that. Similarly, if we say this is a vec, same thing, hairy data vector ref. Whereas if I do, oh yeah, actually that's weird. It should know. It should know the length. It should know the length. That is actually frustrating. Yeah, so if I do, that's z of a. If I do vec. Oh, and that's just calling z. Really? That's just gonna call z. You're not even gonna inline that for me. Really? SBCLY, what are you doing? This is the same code that you were using, right? Oh god, what now?
Should be.
Yeah, that's weird. It
What version
should.
are you on?
Lisp.
It's a function.
Or 8.
Yeah, I mean, that's not very old.
That is weird. 1 second, I need to look at my assembly policies. Yeah, no, that's right. That should be giving me something nice and speedy. And it should see that this is a vec. Okay, 1 second. What's that? Lambda a declare vec a. Clearly there is something wrong here. Undefined function z. Oh god, I'm an idiot. Vec z.
That'd be why.
We've been conc name nilling all day, and I just keep forgetting. The problem with IDIS, of course, is it does something weird that suppresses the error message. That is the trouble. You see that an error happened, but you don't see what it is unless you actually run the thing in the REPL here and you ask. But anyway, so there's that. Whereas if I aref2, I get a call to hairy data vector ref. If I were to guess, that's because the type of this is a it's because the type it's seeing is just it's some vector of single floats, right? So if I were to do simple array single float 3, we would get that exact code, right? That code right there. Rename my assembler and vec and C.
Well, couldn't you just use aref actually too as well? I mean,
vec C.
Oh yes, you're right. Thank you. Also, apparently I have broken part of my interactive disassembly sometime in the past. I'll fix that eventually.
Time to debug your debugger.
Yeah, no, it's not seriously broken. What it is that it's supposed to use named inspectors, which means that I can have multiple of these. That's what the name here at the front is. That's why I've got this one as A and that one as B. It's not like so I can have recursion or anything like that. Although I could do that in principle. I'm just not. It's supposed to use multiple inspectors. But anyway, so, we have this, and we have that. And it's the same code.
Let me see.
Right?
So why is that one the same?
Well, because vec z here, it knows precisely what the internal layout of this is, right? Whereas, and so when this def struct, compiled that, let's see what this looks like. Dear God, that's a lot of nonsense. Here we are, vec z. See? Simple array, single float, star, right? And then it says, oh God, that's weird. Oh, this is probably it seeing both the type of the vector and the type of the slot and ANDing them together, if I were to guess what that is. Yeah,
so what was the assembly before that didn't match up then?
The assembly before that doesn't match up is when you use is IDIS C. Is when you do this. That is different. That is a hairy data vector ref.
Oh.
Yeah.
Oh yeah, that makes sense.
You see it?
That explains why I'm getting the same assembly in my code, because I actually let me share my screen.
Because of your def type?
Yeah. Can you see that?
Yep.
I have a def type vec, which I declare.
Yeah, and
then all my functions to claim that to be the f type.
Yeah, and so because you're manually declaring that type that way, it overrides the fact that what SBCL is otherwise declaring that type to be is vector single float, right? And that's not a simple vector; it's just a vector. And because it's just a vector, SBCL has to hairy data vector ref it, right? Because a vector can be adjustable, right? Whereas a simple vector can't.
Right.
And so SBCL has no choice but to, when it just sees, well, it's a vector of single floats, it can't inline the array accessor for that.
Okay, so it's good to know that my type plays more than just, less code to type for my F-type declarations.
Yep.
Cool.
However, so my other thing, though, right, was, and if you'll let me take back over the stream for a moment.
We can't both be sharing?
Nope. Sadly.
I'm stopping. Stop.
Okay. I mean, in principle, I don't think there's anything stopping us both from sharing, but of course, only one of us can actually be on the YouTube stream at once.
Yep.
I do want to check one other thing, which is this other vec. I'm not going to do that. Let's see. So this is that. And what happens if I do this? The other vec. It'll probably look a little different. Other vec-z. But not by much.
I think
just changes the offset.
Yeah.
Right? All it does is changes the offset it's looking at. And maybe not even, no, you see
9 versus 21.
Yep. And that's the type tag. Right? Because when you have just a simple array of single floats, the type info is much simpler. Whereas when you have a proper structure, the type info is a little more complicated, and so the actual object is a little bit bigger. It may also be that it's not packing it quite as efficiently when you have a full struct versus when you're packing it vector-wise, because it doesn't know that these are all going to be exactly the same type.
But you're specifying it has the same
right,
type there.
Yes, but SBCL may not be clever enough. One of the things that I've heard is that SBCL's struct packing algorithm could be a lot smarter than it is.
Okay, gotcha. So you're saying that it might be a limitation in the way it's handling reading that def struct definition that's specifying the type information on the vector. So when it's transferred
for what?
For converting it, because you're saying that it's generating different disassembly actually.
No. So we have a couple of different things we're looking at here, right? So when we're just looking at the struct that's really just a vector, like it just implements a vector, right? When we look at these three different bits of disassembly, when we declare the variable to be an actual simple array and we do the aref, it inlines that array access, right? When we get our struct that's actually just a vector, and note we're back to RAX plus 9 here. When we look at our struct that's just a vector and we use the actual accessor function, it's the exact same code as if we declared the array type properly and we use the aref accessor. When we just use the vec type that SBCL generates here and we use the aref accessor, it cannot inline that array access, because SBCL sees it as just a vector, not as a simple array, and vectors can be displaced, vectors can be adjustable, vectors can have fill pointers, all kinds of crazy nonsense. And so it has to do this hairy data vector ref here, which is all that smart logic for dealing with the more complicated vector type other than simple vector. What I'm showing down here is that when you use a regular struct and you look at its accessor, it looks almost exactly like the inlined array accessor. It's just the offset is a little different, and that's because the packing is a little worse and the type info takes up a little more space. But otherwise, like efficiency-wise, it shouldn't take any more of your runtime to use a regular struct.
No, it won't take any of your runtime because all that's doing is just an offset calculation prior to doing the memory access.
And it has to do the offset calculation either way.
Right, exactly.
And so my point is that there are advantages to using a vector struct, a struct that actually is just an alias for a particular way of making a vector. There are advantages to that. It could be slightly more efficient in certain cases. but I'm fairly confident that actually for most cases the difference between just using that and just using a struct is pretty negligible. At least on SBCL. It may make some math calculations slightly different depending on how smart SBCL is at loading things into SIMD registers, because like SBCL is actually really clever when you do vector math operations to load things into SIMD registers. But I've not actually checked how good it is doing that when you're just using a vector that has a certain number of single float slots. So that's something to definitely test. I mean, actually, I could check that right now. Let's see, SP. Let's take A is a vec and B is a vec. See what happens if we make vec A, or let x be vec. Oh, I hate generating random code on a stream. Vec x A, vec x B. I'm fairly confident that if I do this for all of those, SBCL will inline stuff well enough. If I do this and then I make vec x is x, y is y, and z is z, I'm fairly confident SBCL will actually use, a whole bunch of SIMD trickery.
Yeah, it does. Okay.
Yeah. It does some other stuff because it needs to be clever, but it does SIMD trickery. This is actually the adds and the mobs right here. This is it doing all of that fun stuff. Like, that's why you see there are 3 adds there. And here's it actually constructing the object. This is allocation in SBCL. This is thread safe allocation. And so that is efficient. What I don't know is what happens if I do it with my other vec. I am not going to do that.
Wait a second. Well, move SS is a SIMD instruction, right? Well,
yes.
Once you know the base pointer, or once you moved it, wouldn't you be able to use a vector operation and save those 3 add instructions? Wouldn't you be able to do just one?
Yes, it ought to, actually. In retrospect, it ought to be doing those all on a single add.
I'm just like, what?
That's interesting.
That's not right. If you're
that disassembly looks weird to me now. now that I'm looking at it a little closer, you're right. That is odd.
That doesn't.
SBCL should be cleverer about that. What happens if I declare these as simple array, single?
You really like simple array, don't you?
And that's why I did
way too much simple array.
I'll be that for about 500 functions in my math
library. 3. Okay, so what I'm going to just call that svec so that I'm not overriding the.
Actually, there's a different namespace for types, so it doesn't matter.
Yeah, there's 7 namespaces according to PAIP, which we need to cover.
Yeah, you can have it's a separate namespace. You can do vec and vector structs too.
Okay, so let's see if we do vec versus svec.
So we have 126 bytes here, 119.
We still have 3 adds. But we lose a little bit of the initialization stuff.
Yeah, we do lose some initialization stuff. That's what. But the 3 adds is really bothering me. I'm just like, why?
Yeah, that is strange. I don't know. Something to ask the SBCL devs. It should be cleverer about that.
I need to go into IRC one of these days and check.
Let me see. What operation are you doing? I'm not looking at your screen. I want to just try my own math.
I'm doing an element-wise add of 2 vectors, and then storing the result in a new vector.
Element-wise add. Oh, okay. Just a sec.
And I'm just looking at the
it should actually recognize the offsets in the call graph. Well, not call graph. Sorry, the control flow graph.
Yeah,
recognize
it ought
the
to.
fact that
Well, SBCL doesn't have a control flow graph per se.
It
but
doesn't.
That's a story for a much different stream.
Oh God, I shouldn't say things that would end up resulting in. Oh, that's a totally different conversation. A long conversation.
Yeah. SBCL, technically speaking, it has something you could call a control flow graph, but there's no explicit step in the SBCL compilation process that you can like point at and say, there, that's the control flow graph right there. No, there isn't one.
Oh, great.
SBCL, like most Lisp compilers, is its own thing entirely.
Okay, so you're doing something like this. Hold on. Share.
Are you going to share?
Something like that?
Give me a second. Sharing.
Yeah, he's sharing. We're both sharing now.
Gotcha. Okay.
Yes. Yeah.
Okay, so wrap that in a function.
Yes. Lambda.
And then disassemble that. I hate this new completion framework.
Oh, I'm having the same. I thought it was just me. I thought me configuring it. I see that you're having.
It's not you.
Thing.
There's a bug on the sly layer that I just haven't gotten around to fix.
Okay. I thought it was when I was messing around with it. I was like, why is it
star? And we have 3 moves. Or no, 2.
Three adds, though. That's the question. How many adds are there?
Oh, there's only 1.
No, there's 1, 2.
Oh. Together, there's
3 adds.
3. Yep, you're right.
Yep, 3 adds.
Yeah. Oh,
so that's weird.
That is
weird. It ought to be clever enough to do that as a single ad. Oh, well. My faith in SBCL is a little weakened. But anyway, let me look at this here. And it looks pretty much exactly the same, right? If we use the implementation that uses vectors versus the implementation that uses structs, the only thing that changes is the offsets.
Yeah, that much is for sure. There isn't much in terms of the memory access but there is a difference in some initialization code. It seems to copy stuff into.
Well, that's just depending on what types we're using.
Right. Okay. That's okay. That makes sense.
Right. Are you looking at my screen right now? I'm not sure.
Hold
I'm not sure looking where.
I'm looking at yours now.
Yeah. So if we use the vec type there, we get some extra initialization. Whereas if we use the svec, which is the proper one, we lose that initialization code. If we use my other vec here, which is the one that's just a struct, it looks pretty much exactly like as if we'd use that svec type, except the offsets are different.
Gotcha.
Right, and so my point is that unless you actually need, unless you really care about the memory usage, right, from using a vector versus using a struct, or if you really need to be able to pass it directly to something that's going to call a ref, right, or something like that. I personally think that there's no particularly good reason to use a vector-implemented struct over a regular struct, especially given that a regular struct gets you type info, and so you can actually do things like, typecase, right?
I agree. Especially if you're going for the full complete math library and you need to differentiate at compile time between a vec4 and a mat2.
Right. Yeah, because a vec4 and a mat2 are both just single float vector 4s.
Yeah. But the reason, I don't know. Are you looking at my screen?
I am now looking at your screen.
The whole reason why I use a vector struct is this with components macro, which allows me to basically generate symbols, as you can see, v1x rather than aref vec 0. You could basically do the same thing with aref though, inside this macro, just using symbol macrolet. So there isn't really a good reason I chose it. It's just a lot less code than doing it manually.
Yep.
I guess.
Yeah. I'm just saying that
But the point of this conversation is that structs do have their purpose in common.
Yes, they do have their
structs
purpose.
They don't get much attention these days because people really don't care much about speed for live coding practices.
Yeah.
And that's what Lisp is good at, is live coding mostly, and flexibility of defining your own language and macros. But, structs have purpose.
Yeah. If you're writing libraries that other people are going to use, those other people will want those libraries to be fast. Those other people might even be you in the future, and you will want that library to be fast. And
99 out of 100, though, just use a class. You're going to
for most
as we saw on the stream today with me corrupting the definition was like out of sync with the image.
Yep. Yeah, actually, there's some really terrible things that you can do with a struct, because when you define a struct, it actually informs the SBCL garbage collector of the layout of that struct, right? As opposed to doing something dynamic with classes where it looks up the type info as it's trying to deallocate. With structs, it actually just informs it. When you define the struct, it informs the garbage collector about how to deallocate that struct. Which means that if you relay out that struct and you already have existing instances, I'm sure there's something in there that SBCL does to deal with this, because I've never actually seen it break. But I'm pretty sure if they didn't have a bunch of special extra code in there to handle that, and I don't know if every implementation would, you might run into cases where it improperly deallocates a struct because it was using the new layout information that you've provided on an old instance of that struct. Right, and then you get into all kinds of craziness where you're allocating and deallocating things incorrectly, and then you really blow stuff up.
Yeah. So
this has been a very, very interesting conversation.
there are a lot of reasons to be very cautious with structs, but occasionally they're the only way, apart from just using vectors directly, to make something actually efficient. And sometimes that's necessary. So
yes.
Structs have their place.
Absolutely.
But be careful. Prefer classes in general. Anyway.
So next episode, we'll probably start by implementing the renderer, which, I can demo an old version right now just to show you what it would look like. This is using the sketch library.
You may need to actually load. I don't know if you loaded crawler into your Lisp image. Oh, you did.
Yeah, he did.
So yeah, we make a stage, and we'll use the defaults, or maybe we won't.
Undefined function.
Wow.
Yeah, something's wrong.
So we'll
leave that for next week.
We'll leave that for next week.
That for next week, everybody.
We end on a demo. But no. Thanks a lot, Michael.
Lifeguard, though.
It always happens. It's okay. Thanks a lot, Michael, for showing us this. This has been a very enthralling conversation, especially the type stuff. I cannot, express the thanks on this, because I think the type system is something that we need to discuss, and we sort of touched base on a little bit towards the end here on top of your app dev, but your examples on structures versus classes really kind of shows off some of the nice features of.
Yeah, I think we need to do some talking on class just in general, some of the more in-depth design patterns of class, in a sense, if we even want to call them that. Stuff like that. We also should have some time we set aside to talk about just optimization, just in general. And in both of those discussions, we're going to get back to talking about the type system at least a little bit. Right. Yes. And I think that'd be valuable.
I think that's going to be the next topic, really, because class is really something that we need to really explore, to really understand it, and from the standpoint, from my interest in it, is how it really integrates, functional patterns into the language, and how you would leverage it is definitely something that we should discuss, because a lot of newer languages have sort of adopted this. Hey, we're integrating functional programming with object-oriented programming. We're multi-paradigm stuff. Well, Common Lisp had it for a long time. It's very opinionated and has a different approach to it. And being aware about it will certainly, make you pick the right features of the language that you're currently even using, because there are similar features there. Anyway, until next time, thanks for joining us. I'll see you guys next Monday.
Yep.